Now that we have successfully georeferenced our Google Earth satellite image, I would like to demonstrate some handy ArcPro tools to take some quantitative measurements of the SP Mountain scoria cone and lava flow, and to better understand the geology and 3D architecture of our mapping area. In this video, we will learn how to measure distances and linear trends using the Measure tool. We will generate 2D topographic profiles using the Profile tool, and we will generate and label topographic contour lines. Step 1. Underneath the Map tab, navigate to the Measure tool. We can use this tool to measure the dimensions and orientation of the SP Mountain lava flow. The Measure Distance window will pop up, and then you simply click to add vertices along a line. You may click multiple vertices along a path, and the Measure tool will record the length of each line segment in a table. It will also sum the total length of all line segments. To complete a line, you must double-click on the last vertex. Here we learn that the lava flow extends from the SP scoria cone to a distance of 7,000 meters or 7 kilometers. You can quickly change the unit of measure by using this drop-down menu. Note at the bottom, it also gives you a path net bearing of 16 degrees azimuth. Since we know that the lava flow originated from the scoria cone, we can use this net bearing to describe the general flow direction, which is roughly south to north. If you want to clear the current results and make a new measurement, click the eraser button. Let's now measure the maximum width of the lava flow. Here we see that it is approximately 3.75 kilometers. The Measure tool is extremely handy when working with remote sense data because you can make accurate measurements of geologic features without having to visit the field site. The Measure tool is great for measuring distances and measuring trends of linear features such as faults. Step 2. Let's learn how to generate 2D profiles or cross-sections along our map. Navigate to the search bar at the top and search for the Profile Ready to Use tool. Clicking on this tool will bring up a geoprocessing pane on the right-hand side of the screen. The first thing we need to do is click on the pencil icon to draw our profile line on the map. Note how a new line feature class is added to our contents pane called Profile Input Line Features Lines. Just like the Measure tool, you must click to add vertices along your profile line. To finish the line, you must double-click on the last vertex. Now that the profile line is drawn, navigate back to the geoprocessing pane on the right. The only field we will modify is the DEM resolution, which I always set to finest when making a profile. Then click Run. Upon completion, you will see that another line feature class called Output Profile has been added to the contents pane. If we close the geoprocessing pane to view our catalog pane, we see also that 2 new items have been added to our geodatabase. The first is the Profile Input Line Feature Lines and Feature Set. Feature set is actually referring to what is shown as output profile in the contents pane. The symbol next to them indicates that they are line feature classes. I will discuss more about feature classes in an upcoming video. This current naming scheme is not super intuitive or descriptive, so let's adjust it to be something that has more meaning to us. Right-click Feature Set in the geodatabase and click Rename. We will call this first one Profile A. We always want our contents pane to be organized and all feature layers to have a consistent and meaningful naming scheme. To clear up some of the clutter, right-click and remove the 2 feature classes in the contents pane that were auto-generated by the Profile tool. Now, navigate back to the geodatabase under the Catalog pane, right-click Profile A and click Add to Current Map. Now that we are more organized, let's generate our Profile A 2D cross-section slice through the SP Mountain scoria cone. To do this, right-click on Profile A in the Contents pane, click Create Chart, then click Profile Graph at the bottom. This will bring up a chart window underneath your map with your topographic profile. Elevation above sea level from your digital elevation model is shown on the y-axis, and the horizontal distance from your profile line is shown on the x-axis. Note the chart properties pane on the right-hand side of the screen, indicating that the units for both axes are in meters. These units of measure can be changed by clicking on these drop-down menus. Earlier, we used the measure tool to measure distances and trends. The profile tool allows us to accurately measure heights of geologic features. By drawing profile A through the SP mountain, we can see on the eastern flank that this scoria cone stands over 240 meters tall, which is over 800 feet. The asymmetry of the cone in this profile is explained by the fact that SP Mountain actually erupted out of the lower flanks of a pre-existing volcano to the west. Similar to Microsoft Excel, you can edit other chart properties in the pane to the right, including changing to a dark background, as well as editing the title and axes names. Here I will rename the chart to Profile A. If you want to export your profile to draw subsurface interpretations in another program such as Adobe Illustrator or InDesign, you have the option to export your chart as a scalable vector graphic, JPEG or PNG. Typically, geologists like to show cross-sections without vertical exaggeration, meaning that the vertical and horizontal scales of the profile are equal. One way to attain no vertical exaggeration is to export your profile as a scalable vector graphic file. Then you can rescale the chart in Adobe Illustrator using a fixed grid to make sure that the vertical and horizontal scales are equal. Now let's repeat this process and draw another profile to get an idea of the thickness of the SP Mountain lava flow. Again, search for the profile tool at the top. Click on the pencil, and this time let's draw a profile across the northern part of the lava flow. Change the DEM resolution to finest and click Run. Again, we will have two new feature classes added to the contents pane and to the geodatabase. We can delete the profile input line feature lines, then rename feature set to Profile B. Right-click and remove Output Profile from the Contents pane, then right-click Profile B in the catalog and hit Add to Current Map. Now right-click Profile B in the Contents pane, click Create Chart, then Profile Graph. You can check the elevation of any point along the profile line by hovering your cursor above the point of interest. From this profile, we see that the SP Mountain lava flow is approximately 40 meters thick, or 130 feet at its northern extent. Like before, I will rename this chart to Profile B to be consistent. Let's draw one more profile to understand the relationship between the Kaibab limestone and the SP Mountain lava flow, as well as evaluate any geologic structures. This time, let's draw the profile line across nearly the whole east-west extent of our mapping area. Again, delete profile input line features lines, rename feature set to Profile C. Add Profile C to the current map, then right-click Create Chart to construct the profile graph. Profile C is quite a bit more dramatic than the first two, which focus solely on the characteristics of the SP Mountain scoria cone and lava flow. Like Profile B, we still see the thick SP Mountain lava flow in the eastern part of the cross-section. I have alluded to there being north-south trending faults in previous videos, but the Profile tool elucidates this geologic structure most clearly. This structure is known as the SP graben. A graben is a piece of Earth's crust that is shifted downward in comparison to adjacent crust known as horsts. which are shifted upwards. Between the graben and its adjacent horst are bounding normal faults that dip towards each other. We can see that the graben walls are asymmetric. The western escarpment stands approximately 60 meters high, and the eastern escarpment is not as high, only about 30 meters above the graben floor. Horsts and grabens are typical geologic structures in regions with an extensional tectonic regime, such as rift valleys. Our study area in Arizona is not situated in a rift valley, but the region has experienced extension in the Miocene. Also, there is a considerable magma chamber underneath our study area that is responsible for erupting the volcanic features of the San Francisco volcanic field. The intrusion of this magma chamber is likely the culprit for deforming and expanding the overlying rock units. Notice how the SP Mountain lava flow spills into the SP Graben at two locations. Since the lava flow conceals parts of the eastern bounding fault, we know that the SP Graben structure existed prior to the eruption of SP Mountain. Understanding the 3D architecture of your study area is important before you begin any geologic mapping or cartography. From 3 simple profiles, we attained some quantitative data on the dimensions of the SP Mountain scoria cone and lava flow. We identified a graben structure in the Kaibab limestone and learned that this structure predates the SP Mountain eruption. One last housekeeping item before we move on to contour lines. Profile A, B, and C are named consistently in our geodatabase and our contents pane. To keep the contents pane tidy, let's create a new group layer called Profiles to house profiles A, B, and C. Now let's move on to step 3, creating contour lines. Contour lines represent areas of equal elevation. A map with contour lines is known as a topographic map. Topographic maps provide an accurate representation of the land, including its elevation, slope, and natural features. Adding contour lines to our map will help us and others viewing our map to visualize the landscape in 3 dimensions. To begin, navigate to the search bar at the top and search for the Contour Spatial Analyst tool. This will bring up a geoprocessing pane on the right-hand side of the screen. First, specify the input raster to be the digital elevation model. Here, we must decide on the contour interval, which is the vertical distance or difference in elevation between 2 contour lines. Having a larger contour interval will result in less contour lines on our map. Conversely, having a smaller contour interval will result in more and more closely spaced contour lines. For this example, I will specify a contour interval of 10 meters. For the output feature class name, we want to rename it to be meaningful and consistent with our project. I changed it to contour 10 meter and assigned the SP project prefix to the name. We can leave the other fields as they are and run the tool. If you haven't already, toggle your satellite image off in the contents pane. Contour lines look best draped over top a hillshade. Now we need to add some contour labels so people can know the precise elevation of features in our map. To do this, right-click SP Contour 10 meter in the contents pane and click Label. Note how the numbers appear along the contour lines. However, they are not remotely accurate to the real elevation values. To fix this, we must again right-click on the SP contour and then open up the labeling properties. The main things we need to pay attention to here are the fields and the expression. The SP Contour 10 meter feature class has 4 fields: Object ID, ID, Contour, and Shape Length. All feature classes have fields that define certain attributes. I will discuss more about feature classes and fields in an upcoming video in this playlist. If we look at the expression box, we see a default piece of code that is telling the program to label the contour lines on our map based upon the ID field. We need to change this expression so that the program labels the line based on the contour elevation field. To do this, simply highlight and delete the old expression, then double-click on the contour field to write a new expression. Now, when we hit apply, the contour lines on the map are accurately labeled with their elevation above sea level in meters. Note how the contour number labels redraw each time you zoom in or out of your map. Each time you run the contour tool, it will randomly choose a color for your contour lines. If you want to change the color of them anytime, navigate to the Contents pane and double-click the line symbol underneath the SP contour layer in the Contents pane. This will open up the Symbology pane. Migrate to the Properties tab. It is here that you can adjust the color and line width of your contour lines. Be sure to click Apply at the bottom. That's all for this video. In the next video, I will show you how to create a local scene to further view your data in 3 dimensions.